In the previous lecture, we saw that materials for products and structures can be divided in four main groups: metals, polymers, ceramics, and composites. Two groups were not useful for high-strength structures: polymers because of their limited mechanical properties, and ceramics because they show very brittle fracture. The remaining two groups, metals and composites, are the focus of this lecture. Let's start with the group of metals. Metals can be found in the crust of the earth, so mining activities are applied to retrieve these so-called ores. These ores, like iron ore or bauxite, are transported to factories where the metal is separated from rock, sand, or other substances. We call these processes a blast furnace in case of iron ore and electrolysis in case of bauxite. Both processes use very high temperatures and the metal is obtained in a liquid state. Further processing of the molten metal is aimed at purification of the metal, removing all the unwanted elements, and alloying. Alloying is adding elements with a specific purpose. The alloying elements should increase certain properties of the base metal. For example, the strongest aluminium alloy is 5 times stronger than the pure unalloyed aluminium. When the metal alloy has the right composition, the material can be cooled down. Often a number of casting and rolling processes are performed on the metal alloy. These processes shape the metal alloy in semi-finished parts, like sheets, plates and billets. The next step is to transform these semi-finished products into final products by manufacturing processes. This will be explained later. Metals and their alloys have a number of attractive properties. Most metals can be treated as isotropic. So the question to you is, what is isotropic? What does it mean? It means that the properties are independent from the directions in which the material is tested. Also, metals can be strengthened. By adding alloying elements, the strength can be increased. Also, metals show plastic behavior and they can melt. Both characteristics are important for manufacturing processes. For metals, processing in general is very good. Not only forming and casting, but also machining and coating. And last but not least, metals are often cheap. I already mentioned a few times the word mechanical properties. Let's look at two rods of different materials, X and Y. If you look at the maximum load, then you know rod 1 is stronger. But is material X also stronger material than material Y? In order to answer this question, we need to make a fair comparison. We see that rod 1 has a larger cross-section A than rod 2. This means that there is more material to carry the load. So a good measure would be to compensate for this larger cross-section and divide the load by the cross-sectional area of the rod. In this case, we get the so-called stress of the material. The stress is the force divided by the cross-sectional area. The symbol for the stress is the Greek letter sigma. Note that the cross-section is perpendicular to the working line of the force. Another important property is the strain, which tells something about the elongation of the material due to loading. In this case, we have to normalize for the length. So we divide the change in length by the original length. The symbol for this strain is the Greek letter epsilon. Both stress and strain are very often used in discussions about mechanical properties of materials. A typical example of the use of mechanical properties like stress and strain can be seen in this table. The table gives the tensile test data for different metal alloys. In the first column on the left, you see a number of different metal alloys. In the second column, the density of these materials is given. Next to that, the elastic or Young's modulus is given, which represents the material's resistance to deformation. Column 4 shows the yield stress, the stress when plastic deformation starts. And column 5 gives the failure strength, the strength when the metal alloy fails. The last column shows the value of the failure strain, the maximum strain at which the metal alloy breaks. For aircraft, we know that besides the strength and stiffness, also the weight is very important. That's why we usually work with specific properties. In case of the tensile loads, the specific property can be obtained by dividing the property by the density of the metal alloy. Look at the numbers in red. Notice that some materials that had high property values now have much lower specific property values. You can see that, for instance, for steel alloys. Another striking feature is that the stiffness, or E modulus, for all metal alloys is more or less the same, about 25 gigapascals. Note that the formula for the specific property might be different for other load cases. Be careful for this. Polymers are not very interesting for structural applications. Nevertheless, I would like to discuss them here because they are a very important ingredient of composites. Most polymers are man-made materials, synthesized from refinery products or crude oil. Those monomers are processed to become macromolecular substances. There are two types of polymers which are of interest: thermoplastic and thermoset polymers. Thermoplastic polymers, see the picture above, are made of long molecular chains which don't have strong bonds between the chains. The chains are made of one component, one type of monomer. Due to the weak bonds between the chains, the polymer weakens when the temperature increases, and when cooled down, the polymer becomes rigid again. This softening is reversible. The second polymer type, see picture below, is the thermoset. Thermosets are made of more than one type of monomer. Usually the different monomers react and form large molecular networks. In this case, there are strong bonds between the chains and they don't want to weaken when the temperature increases. The cross-linking or curing of these polymers is irreversible. Looking at the properties of polymers, we see that polymers are isotropic, just like metals. We also see that polymers have a low strength and stiffness. Furthermore, the diversity in polymers is huge. There are many different specific polymers. Polymers are also easy to process. In case of thermoplastics, they can be melted and they have a significant plastic flow. In the picture, you see an injection molding process, a process that is very widely used in the plastics industry. Also, the base polymers are usually very cheap materials. The next material category are composites. Composites are composed materials, materials made of more than one constituent. Often a composite is made of fibers and a resin or a matrix, and the resin is a polymer. For the fibers, we can choose between different types: glass fibers, carbon fibers, or synthetic fibers like aramid or Dyneema fibers. Fibers are also available in different lengths. Short fibers with a length of a few millimeters, long fibers with a length of a few centimeters, and so-called continuous fibers with a length of meters. For aircraft structures, we usually use continuous fibers. Next, there are also hybrid materials. They are made of metal layers and composite layers. The material named Glare, which is developed at TU Delft, is a good example of a hybrid material. The fibers and the polymer resin in a composite have different functions. The fibers are strong and stiff, so the mechanical properties of a composite are dominated by the fibers. The fibers are embedded in a polymer resin, and the resin provides protection for the fibers, support for the fibers, and the resin transfers loads between the fibers. Fibers are strong and stiff in one direction only, in length direction. That means that one layer with continuous fibers will be anisotropic. A composite usually has multiple layers. The orientation of the layers in a composite laminate determines the degree of anisotropy of the laminate. Let's look at a number of properties of composites. For example, composites can be highly anisotropic. And you may ask yourself, is this an advantage or a disadvantage? You can use the anisotropic behavior to your benefit if the loads on the structure coincide with the fiber directions. This is called tailoring of the composite material. Composites are often layered materials or laminates. And composites do offer a high strength and stiffness in fiber directions. For most composites, the density is low due to its constituents. The density is usually in the range of 1500 to 2500 kilos per cubic meter. And realize what the density can do in the specific material properties. Composites are usually costly and show very little or no plastic behavior. Those are disadvantages. But the processability is usually good. We may work with prepregs where the resin and fibers are already mixed. Most composites can also be draped easily in a mold, just like fabrics. In composite structures we see two main material concepts: laminates and sandwiches. Laminates are made of multiple composite layers stacking together. The final thickness of such a laminate is usually small, in the order of a few millimeters. The other concept is the sandwich. In the sandwich we see two face sheets, which are thin laminates, and a core material in between. So the core is sandwiched between the face sheets. The core material can have a honeycomb structure, or it can be a foam. Sandwiches are often used when a high bending stiffness is required. The height of the sandwich has a large impact on that bending stiffness. At the moment, two new aircraft have entered the market. The Boeing 787 a couple of years ago and the Airbus A350 just recently. Both aircraft apply composite materials in a large part of their structure. About 50% or more of their structure consists of composites, mainly carbon composites. These aircraft are also the first aircraft where carbon composites are used in the primary structure. Thus far, composites were mainly used in secondary structures. In this lecture, I gave some detailed information on the most important aeronautical materials, the metal alloys and the composites. I also introduced the concept of specific mechanical properties, which is important because we need to create lightweight structures. Next time, I will discuss a few items of the manufacturing of these materials.